Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on February 24th, 2026, just yesterday. It introduces a new testbed called Chain that shifts the focus from passive visual question answering to active, physics-driven problem solving, finding that even top models struggle to plan actions when faced with real-world geometric constraints. The paper is titled, From Perception to Action, an interactive benchmark for vision reasoning. And, as we'll see later, the results expose some significant blind spots in how current large models understand the physical world. And for those interested in the implementation, the authors have shared their code on GitHub. Figure 1 illustrates the core shift in evaluation methodology proposed here. The top panel depicts the traditional visual question answering setup, where a model passively observes a static image and outputs a text description. While it might recognize a puzzle, it never has to prove it understands the internal mechanics. In contrast, the bottom panel outlines the chain paradigm. Here, the system must engage in a continuous loop, observing the state, planning a move like pull the red piece, executing that action, and then processing the physical feedback. So Figure 2 details the construction pipeline, which is split into 3 key stages. Step 1 on the left focuses on sourcing and filtering. The authors select puzzles that strictly require sequential reasoning and validate their difficulty through expert human playtesting. Moving to the center, Step 2 shows how these puzzles are implemented in engines like Unity to create a standardized environment with multi-view observations. Finally, Step 3 on the right illustrates the closed-loop evaluation, where the agent continuously perceives the state and executes atomic actions, while metrics track success and efficiency. With the pipeline established, Table 1 reveals the main performance leaderboard. The results show a clear hierarchy, where GPT 5.2 leads the pack with an overall success rate of roughly 23%. Crucially though, the columns for puzzle and stacking expose a massive capability gap. While the best models solve about 31% of stacking tasks, success on the mechanical puzzles collapses to just 3%, confirming that interlocking geometries remain a major stumbling block. On the open source side, Kimike 2.5 stands out as the strongest competitor, matching some of the mid-tier closed models. Well, if the numbers in the previous table seemed abstract, Figure 4 provides the visual proof of these failures. It challenges leading video generation models, often called world models, to generate a valid disassembly of a Lubin lock. In the top row, with a simple 2-beam setup, models like Sora 2 and WAN 2.6 struggle to maintain rigid bodies, often merging or distorting the beams. Then in the bottom row, which features the complex 6-beam lock, the outputs collapse completely. The models, including Kling 2.6 and Hunyun Video 1.5, begin to hallucinate random blocks and violate basic interlocking rules, showing they are not yet true physical simulators. Alright, moving on to Table 3, the authors ask a critical question. Does the model actually need to interact, or can it just plan everything from the start? The table contrasts the standard interactive performance on the left with a one-shot setting in the center, where the agent sees only the initial state. The drop is massive. For instance, GPT 5.2 falls from roughly 23% success down to just 7% when denied interaction. In fact, if you look at the puzzle column under one shot, every single model scores 0. This proves that static planning is insufficient. Agents must actively probe the environment to discover hidden constraints. To understand the nuance of these failures, Table 2 breaks down the accuracy by difficulty tier. On the right, under stacking, we see a typical degradation. The easy tasks are effectively solved, with GPT 5.2 and Sonnet 4.5 hitting 100%. But as the complexity rises in the hard column, performance crashes to single digits. The situation is even more severe on the left, under puzzle accuracy. Here there is no easy win. Models manage only 10% on easy puzzles, and for the medium and hard tiers, every single model scores a flat 0. This confirms that while simple stacking is feasible, the hidden constraints of interlocking puzzles create a barrier that current models simply cannot cross. Wrapping up, 2 takeaways stand out. While models excel at passive observation, they fundamentally struggle to translate that into effective, physically grounded actions. The chain benchmark exposes this gap, proving that true embodied intelligence requires more than just scaling up static datasets. That's it for this episode of the AI Research Roundup. I'm Alex, thanks for listening.